Welcome back. Hope you're doing well. We have been talking about matrices a lot recently in this week's presentations. And all matrices are examples of finite dimensional linear transformations. In fact, there's a theorem that says that any sort of finite dimensional linear transformation, namely between a finite dimensional vector space and another, can be written in terms of a matrix. Now, linear transformations are very important to me personally because a lot of my area of research stems from these notions of linear transformation. So we'll be talking about some of these things today. Again, matrices are the things to be thinking about here as we define linear transformations in this way. Now, what is a linear transformation? What we do here is we begin by looking at vector spaces starting from V1 and going from V2. These are just two arbitrary vector spaces here. But we'll say that a mapping between these is linear if we say that whenever basically we'll say that they respect linear operations. If you do addition of the two vectors, then L of x plus y equals L of x plus L of y. And then finally, if you take a scalar multiple of the vector x, then that is going to be, once you plug that into your linear operator, it's just R times whatever you would have had if you had had a linear operator L operating on just the vector x. So for example, if V1 and V2 are equal, we'll call that a linear operator. This is something that I'm a little bit more familiar with, or what these things can look at whenever these two things say our two vector spaces are equal, or when we're working on functional spaces, trying to make an operator in between two spaces where the spaces are subsets of functions on, say, the real set, on the real line. And then a linear mapping that goes from a vector space to just the real numbers is called a linear functional. We'll see some examples of these in just a little bit, but see if you can think of anything here. The one I want you to be thinking of in particular is matrices. If you have a matrix 1, 2, 3, 4, and you're plugging in to this some sort of combination of vectors, like maybe 5, 6 plus 7, 8 as these vectors here, then we know that the way that you can work on the addition of these two vectors with matrix multiplication is that it's okay to distribute the matrix to each of these two vectors. This is L of x plus y in this case, because L is described by the matrix 1, 2, 3, 4. Think of L as the function that is described as multiplying on the left by the matrix 1, 2, 3, 4. Then if you have a scalar multiple inside of here as well, then that scalar multiple is going to get to come outside thanks to how the scalar multiplication works inside of the space of vectors. So everything here is a linear function. This is a linear function between these two vector spaces. Okay, so a remark here to kind of think about here real quick before we move on is that if you're looking at a function from the real numbers to itself, and this is a really good example of thinking of this in terms of one-dimensional vector spaces, is that if you're looking at the function f of x equals ax plus b. Now, in general, we know this sort of formula before because we've seen it as with different letters in here. Y equals mx plus b. This is slope-intercept form. This might be a good place to look in terms of going from a one-dimensional vector space to a one-dimensional vector space, getting a linear functional on this space, because these functions describe lines. That's another thing to be thinking about. Now, the question is, which one of these functions is actually described as linear? Now, let's take a look at what these two things are. Notice that this first one, for example, says this. If I plug in L of 0, well, I know L of 0 is L of 0 plus 0, right? So because of this first condition, I know that I can break this apart in this way. L of 0 plus 0, this is like if my vector x equals 0, my vector y equals 0. If I break those apart into two separate terms, I can write it like this thanks to this condition right here due to this first condition. Well, if I put these two things together, what do I get? L of 0 is equal to L of 0 plus L of 0. So I know, subtracting L of 0 from both sides, that I must have that when I plug in 0 into my linear function, then I'm going to have to get 0. The only time that that works in a function that describes a line in terms of a function going from R to R is whenever b is equal to 0, when your y-intercept of your line equals 0. What happens when you plug in x equals 0? You need to get that y is 0 as well. So the only linear transformations on this space are going to be lines that go through the origin. So that's something specific about what linear transformations are. When you plug in 0 in for them, you're going to get 0 out. So these are the lines that are all translated so that the origin is a point on that line. Those are the transformations that are known as linear. So we could be calling these as linear functions, linear mappings, linear transformations. These are all just names of the same thing whenever we're talking about what these things are. Let's go ahead and see some basic properties of these linear transformations as we go through here. Let's start by letting L from V1 to V2 to V2 be a linear mapping. Now, in the previous slide, we saw that you can add any two things and you can break it apart thanks to the function. If the function respects addition and scalar multiplication, but it also respects it if you do it multiple times. If you do it R1V1 plus dot 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 plus RKVK on the inside here, if you're mixing up both scalar multiplying as well as adding of vectors, then you can break that up so that each term gets its own copy of the function L just operating on the vector itself. And then once you've done that, you can take the scalar outside for each of those functions. So it's okay to go through and do this. Essentially, the way that we get this equality here is we're using the property of breaking up the function by addition, as well as bringing out the scalar for multiplication multiple times to try and get us from one step to the other. We can see this here in this one, for example, starting from the case where we have just two scalars and two vectors. We can start by just breaking apart R1v1 and R2v2 to be inside of each of their own individual vectors. And then now that they're individual vectors, we can bring out the scalars, and that gives us this. But it doesn't stop at two vectors. We could have done this at three vectors by first breaking apart like 2 and 1. We have R1v1 plus R2v2, and then breaking apart the R3v3. Now, we already know what this guy is because we just did him up here. So we can write him like this. So there's a substitution going on there. And finally, we can break apart the R3LB3. It's a little bit of an induction going on in order to kind of see how this might be proven. It's a little proof by induction taking place here. Now, thanks to what we talked about before, in general, if we're not just working in terms of R and R, it turns out that if you're looking at any arbitrary vector spaces, V1 and V2, if you plug in the 0 vector for the linear function that you're working with, then what you get out is the 0 vector in your range space, in your codomain. So here, 0, 1 and 0, 2 are 0 vectors in their respective vector spaces here. So, for example, L of 0, 1 here, if I multiply the 0 vector by 0, I'm just going to get the same thing. So this next step just comes from the fact that I can multiply the 0 vector times 0 in my scalar field and still get the vector 0 inside. But anytime that I multiply times a scalar, it's okay for me to bring it outside. So I can write it like this and get that this ends up being the 0 vector, because 0 times anything now in terms of my second vector field, my V2, is going to be equal to the 0 vector in that field. And then now that we have this, we can say that the L of negative V is equal to negative L of V. That is, if I plug in a negative for a vector on the inside, then the result that I get after doing my transformation is getting a negative on the outside of my function here. So here, it's the same sort of thing. This is negative V is negative 1 times V. I can bring the scalar for negative 1 outside and get this. So again, think about matrices as you're going through and doing this. Matrices work the same way. Lines work the same way. If I have a line here, then this has a lot of symmetry. If I have 0.15 over here on this side of the line, then I know exactly what this point is. Negative 1, negative 5. It should be the negative of whatever it was on the positive side because I plugged in a negative for the x. This is the sort of thing to be thinking about as we go through and look at these linear transformations. More examples here of linear mappings. One linear operator that goes from a vector field to itself is just scaling, multiplying everything inside of the vector field by a specific scalar, like S and R. Remember, in order to show that something is a linear mapping, we need two things to happen. One, it needs to be clear that addition is preserved by this mapping. And two, we need to make it clear that scalar multiplying is preserved by this mapping. So what we need to show is that L of xy equals L of x plus L of y. And what we're going to do is say, okay, well, what does L do? It scales whatever vector it is that you're working with. So we have S times x plus y equals Sx plus Sy by just distributing the S. And finally, by the definition of what L is, we know Lx is Sx, for example. So we get to just replace S of x, or S of x, S times x, if you will, times to be L of X. Same thing with S times Y to be L of Y. Same deal with scaling. We can bring scalars outside. And if you go through and talk about what L of Rx is, then S times R of X, we can always switch these two scalars, whenever we're doing our multiplication. And finally, Sx is Lx. So this is just going through the mathematics of showing that this is a linear mapping. Dot products are linear mappings. So a dot product with a particular fixed vector. We might define a function L sub v naught. Maybe if we want to distinguish that this is the dot product functional, but we are fixing a vector v naught in order to be able to continue. So what it does is it says, okay, take a vector v, something inside of the vector Rn. And now what I'm going to do is say, given what this vector is right here, I'm just going to say, okay, take these two vectors that you have and just take their dot product. What you get is a scalar. You get something inside of the real numbers. This is a linear functional. Linear functional, again, is something that has a range space of the real numbers. We can check to see that the dot product is indeed linear in its first vector here. And so because of that, this is another example of a linear mapping. And then we have cross products with a fixed vector. We could define a function L sub v naught, something like this, where whenever you plug in a vector v, this vector being inside of r cubed, and v naught already being some pre-specified element inside of r cubed, then you can say L of v is just taking the cross product of v with this pre-specified vector v naught. This is the vector product, so you're going to get another R3 element out of this. So this is actually not a linear functional. This one is a linear operator. It comes from the vector field to itself when you do this cross product. And then finally, multiplication by a fixed matrix, the example that we talked about at the very beginning. Multiplying by a matrix, that is a linear functional, or not a linear functional, my bad, a linear mapping between Rn and Rm whenever A is an M by N matrix. So all of these are examples of linear mappings. We can just go through and check the conditions on each of these to see that scalars work very nicely with each of these sorts of operations. The idea is that this sort of theory around linear operators is very rich because lines are very nice to work with, like in R2, and we are generalizing the notion of lines to be now in any sort of vector space. This linear operator is meant to be the generalization of a line in R2. Functional vector spaces, same sort of deal. Starting right up here, we have evaluation at a fixed point is a linear operator. We're now looking at functionals, or this case is a functional, or operators or linear mappings that now take place where we're starting from the space of some sort of functions, like maybe some subspace of the function space, f of r. We can do this in general for the entire function space, f of r. We can evaluate at a fixed point. So f of r going into r, the way that this works is you plug in a function f, and what you get out of it, once you plug in L, is you get function at a fixed point A. So what you do is you say, okay, when I'm specifying what this function is, I'm going to first say, okay, what is the A in R that I would like to plug in? Let's say, for example, maybe it's L of 0, right? So maybe you write 0 here. So L of 0 of this function f, what it's going to do is it's going to say, okay, let's write this to be f of 0. You can see now maybe a little bit more clearly that what you put into the function is a function. What you put into the linear mapping is a function. And what you get out is an actual value. You get a real number out of all of that. So this is a linear functional. We can go through and check again to see that this is indeed a linear functional. For example, when I go through and plug in f plus g for two functions that are real valued, then when I go through and plug in 0 for this function, well, how do I define f plus g? It's just f of 0. In this case, it's just going to be f of 0 plus g of 0. And if it's f of 0 plus g of 0, what's f of 0 equal to? That's L0 of f plus L0 of g. And that's exactly what it means to be a linear functional, at least what it means to preserve addition. The same thing happens when we try and do scalar multiplication times a function. So we get some very nice examples there. Multiplication by a fixed function is also going to be a linear operator this time because we're going from the space of functions to itself. What we do is we start by fixing a function g, and then we define the function L sub g to be taking whatever function you plug in and multiplying it times the function g. We can check to see that addition and scalar multiplication are all preserved here. So this is another example of a linear mapping. But we don't have to just work from the set of functions itself. We can instead look at a subspace of functions and try and define things from there. Remember that we defined C1 of R to be the space of continuously differentiable functions. These are the space of functions f which are differentiable such that f prime, its derivative, is continuous. So that's what it means to be inside of C1R, is that the derivative of the function is continuous. So differentiation is going to take C1 of R and plug it into C of R. How do we know this? We know that it's going to take f and return f prime. When you take the derivative, what happens to a function is you just take f prime. We know that we're declaring that we want our domain space to be the space of continuously differentiable functions. So when we take the derivative, what do we know? F prime is continuous. We know that our range space is going to be the space of continuous functions because what we get out of the derivative function is a continuous function by our definition of our domain. You can check to see that the derivative is a linear mapping. We can take f plus g. If you take its derivative, then the derivative breaks up very nicely. And that's exactly what we get over here. And then if you take scalar multiples, the scalar multiple can come outside of the derivative sign. Basically, any scalar multiple of a function, when you take its derivative, the scalar can come outside. Derivative of 2x squared is just 2 times the derivative of x squared, is what that is an example of that. So this is another example of a linear operator. We're just checking to see that these two conditions are met. Integration is a linear function. This is one that goes from the continuous functions on the reals to the real numbers. This is a linear functional, in fact. And that's because whenever you integrate with respect to a variable, you lose that variable in the process once you go through and plug in a and b. Now, again, for this particular integration variable, we have to specify what a and b have to be beforehand. So we're specifying what are the left and right endpoints for our integral. So what happens is we plug in a function f, and then we integrate this one function going from a to b. If you do this, though, you can check addition is preserved and scalar multiplication is preserved. It's the same notion of if you take an integral and of the addition of two functions, you can break up the integral into being of the two separate functions. You can take scalars outside of the integral. It's really interesting because we have talked about these sorts of operators and functions and functionals throughout all of mathematics so far, but we've never connected them like this. We've never connected them all into the same theory. We've talked about differentiation and integration as two very separate functions, but really they share a lot of properties with each other. Namely, both are linear functions. Same thing with evaluation and multiplication. We've talked about how you do these all the time and how you define the addition, subtraction, multiplication, division of two functions. But they're all related to this notion of linear operators or linear mappings. And all of these linear mappings have properties that we can speak of as if they are all in one big collection. So when I speak about properties of linear mappings, I'm speaking about more than just matrices. I'm speaking about derivatives. I'm speaking about integrals and things like this. I'm speaking about all of these different types of functions here. So more properties here. If a linear mapping is invertible, then its inverse mapping is also linear. So like, for example, if I had a matrix going from V to W, like a matrix going from Rn to Rm, if I take its inverse, what I get is also a linear mapping. It's also an inverse. It's the same thing if you're able to, for example, find the inverse of the derivative map. If you do that, then you know that what you're looking at is a linear mapping whenever you take that inverse there. Now, if L and M can compose nicely, then the composition is also going to be linear. This one's a neat one to check. You can check to see that addition is preserved by the composition of two linear functions, as is scalar multiplication. It can be taken out of both of those functions. Finally, if you take two linear functionals and add them together, again, to be particular here, we have to have it be the case that these begin and end in the same vector spaces in order for this to make sense. Then the sum should also be linear. The thing to be thinking about here is, what if you had two matrices you were multiplying by? 1, 2, 3, 4, and 5, 6, 7, 8, for example. You can think of this one as a linear operator from R2 to R2, and you can think of 5, 6, 7, 8, that matrix as L2, a linear operator going from R2 to R2. So what does it mean to sum two operators together? You just take the two functions and you add them together. If we're looking at matrices, this corresponds to matrix addition. You're just adding these two together. In terms of functional spaces, it's the same thing. You're adding two functions together, going from one space to the other. So the sum of two mappings also ends up being linear. We know this in specific with the case of matrices because when you add two matrices, you get a matrix, and a matrix is a linear operator. Linear differential operators. These are very nice to us because we're going to be talking about differential equations very soon. In fact, we're going to go through the calculus sequence near the end of this course. So we want to know a lot about derivatives and how they work. So let's talk about linear differential operators. Let's start with an ordinary differential operator. Let's take a look at what this one is. Here, L is an operator that involves functions G0, G1, and G2, all of these predetermined smooth functions on R. And then we have these sorts of operators here. Here, d of d sub x is just the derivative operator. It's the capital D that we had on the previous slide. And then d dx squared, you could think of this as d composed with d, right? This is d composed with d. You take the derivative and you take the derivative again. We know that this is a linear operator. Finally, if you multiply these things by smooth functions, multiplication of functions is linear, and then the addition of any of these things is also linear. That means that the differential operator that we're talking about here is itself a linear function. In fact, it's a linear operator. If everything is a smooth function, which recall means that it has infinitely many derivatives, then if you take some derivatives, you have not run out of derivatives. You still have infinitely many left to go. And if you're multiplying times smooth functions, the product of smooth functions is smooth. So everything here is very well defined, and this is a linear differential operator. Another one that you could see a lot in terms of especially working with partial differential equations is the Laplacian, or Laplace's operator. This is one that takes you from the space of smooth functions on R2 to smooth functions on R2. So what I mean by that is that its domain consists of two variables, like let's say x and y. So if I'm taking the Laplacian here, what I end up doing is I end up adding the second derivatives of this function, the partial derivatives of this function, with respect to each of its variables. So what it does is the Laplacian says it takes a function, you plug it in, that's the C infinity of R2, and then it takes the partial derivative with respect to x twice of that function, and then adds to it the partial derivative with respect to y twice. So this is the second partial derivatives with respect to the function, all added together. This is known as the Laplacian, is also sometimes noted as the del operator squared. It's the del operator multiplied times itself. You may be familiar with this if you have some Calc 3 left in your mind and you're familiar with how the divergence operator was defined. So that is the Laplacian operator, ends up being extremely useful in many places in applied mathematics. Linear integral operators. We talked about differentiable ones. What about linear ones? We've already talked a little bit about how you can get the derivative to be a linear, or the integral to be a linear functional if you have a and b to plug in here. But what if instead of a and b, you had another variable to plug in here? Let's say, for example, what you did was you took a function f, and what you did was this. You said, I'm going to take this function f, and I'm going to define an integral operator like this. I'm going to take the function, I'm going to take its integral, and then I am going to make it a definite integral. But what I'm going to do is have it start from a base point like a, and then I'm going to have it go its upper limit for this integral to be another variable x that I need to plug in. That's going to give me a function. That's going to give me a function in that one variable. The variable here is going to be x. That's why you see this little x right here on the left-hand side of this integral. Technically, I would need to plug in that x to figure out what the actual value of this integral would need to be. But that gives us a function. So here's an example of this. I could take x. X is a continuous function. So I could take that function and I can plug in the function L of f. Here, f of x is equal to x. All right. Let me write that f a little bit more neatly. So I could write L of f to be this function. I could write it to be going from, let's say a is 0 here, just to kind of make it standard. And then we're going to say that this L of f is going to be the function of integrating, I'm not going to call it x anymore because I want to put x up here. I'm going to use a different variable. I'm going to call it y dy. Now, the reason I'm putting y here instead of f of y is that I know that what f of x equals is x. Hence, f of y is going to be equal to y. So what I'm doing is I'm integrating y, dy, and then plugging in x. Well, what happens when I go through and integrate this? What I'm going to get is 1/2 x squared. So what this antiderivative operator is doing is it is anti-differentiating. It's taking me from x to 1/2 x squared. It's giving me a function instead of an actual value. So the antiderivative operator says, okay, I'm going to start from a particular base point, in this case 0, and I'm going to take the antiderivative of this with this base point. So the antiderivative of x becomes 1 of x squared. Now, x wasn't really mentioned anywhere here for L of f, and since L of f is a function, I need to add this x here to specify that L of f is itself a function. You plug in an x, and what you get out is 1/2 x squared. Just wanted to talk about that one a little bit because otherwise that could be a little confusing about what variables are actually there, why the change in variables, and things like this. We could also take Hilbert-Schmidt operators that have something called a kernel being multiplied inside of the operator here. So here what you're seeing is you're going to take a kernel operator, which as you can see is a function in terms of x and y. Here, k is just going to be some continuous function that is defined in your x component on the closed interval going from c to d, and it's defined in the y variable as going from a to b. If it helps, you could think of this as just r, and this is as r. But the reason for the restriction here is that it doesn't have to be defined on all of the real numbers. It's possible that they could be defined on just the closed intervals here. And the reason that we specify from a to b is that these also give us finite bounds that we're going to be integrating on. We know that in terms of the differential y, our function k is defined going from a to b. We also know that the function f that we're plugging in for our function is also defined going from a to b. So it's possible for us to multiply these two in terms of their variable y, and then integrate with respect to y. Now, this is only a partial integral. I haven't integrated with respect to x, which is another function inside of here. So you can see here that I have to plug in x to see what this ends up being. This takes me a function over here, which right here is plugged in terms of y, and what it gets me out is a function that is left in the variable x because I've integrated by y. You can see my limits would get rid of the variable y in that expression. This is known as the Hilbert-Schmidt operator, or integrating by a kernel function, and that's what k is right here. And finally, the Laplace transform is a very special type of Hilbert-Schmidt operator. This is a good example of this because we do this a little bit whenever we're trying to solve differential equations. We try to transform functions into things that are easier to find differential solutions for, and use that to try and make differential equations easier. The Laplace transform is an example of this. The Laplace transform takes things from BC, these are the space of bounded continuous functions, going from 0 to infinity, and it takes it to the space of continuous functions, not necessarily bounded. And what this does is it has you multiplying times a kernel. That kernel here is e to the negative xy. That is a function in terms of x and y, and you multiply that times your function f, and once you integrate by y, you only have x left over. So this is a neat little thing that helps us a lot in differential equations. So a neat little trick there. Now let's go ahead and see some other final examples before we finish off, especially ones that are going to be useful for us in the future. Let's take a look at the space of m by n matrices. And let's take a look at the operator known as the transpose operator. Right now, let's just go through and call it alpha. So what this does is it takes us from the space of m by n matrices to the space of n by m matrices. And what it does is it takes a matrix to its transpose. You can check and see the transpose is a linear operator. If you take the transpose of the sum of two matrices, it's just the transpose of each one. And then a scalar multiple can come outside of the transpose operator. Hence, alpha is a linear operator. So this is a good example of a linear operator and some of the things that we've seen before. Here's a non-example that maybe might surprise you. Here is a non-example of a linear operator because this one is quite prevalent. The determinant is not a linear operator. This, again, is not a linear functional, in fact. This, remember, is the space of 2 by 2 matrices going into the real numbers that takes the matrix A and spits out the determinant of that matrix A. How do I know this is not a linear operator? What do I have to do to show this? Well, remember that one of the parts of this is to say, is it the case that the determinant of A plus B is equal to the determinant of A plus the determinant of b. That shows that, got to zoom in to get b here. So we'll just write it like this. Remember that shows that addition is preserved by the determinant. So if that's the case, then we can move on and check for scalar multiples. But in fact, the determinant does not satisfy this property. Well, in order to do that, we need to show a counterexample. Counterexample being, can we find two matrices A and B such that the determinant of that A plus B is not the same as the determinant of each individual matrix? And what we're going to choose as A and B is the basis elements for M22, which is when you have a 1 in the top left corner and when you have a 1 in the bottom right corner, and zeros elsewhere in your two matrices. Now, A plus B is going to be the identity matrix. And in fact, the determinant of the identity matrix is 1. However, the determinant of any of the basis elements inside of M22 is going to be 0, while the determinant of A plus B is 1. So it cannot be the case that addition is preserved by taking this linear functional. So beta is not a linear functional. Now, we've seen a ton of examples here, and these are great things to play around with, see again and again and again as we go through there. The idea here is that we now have a unifying umbrella for all of these types of functions and functionals and operators that we've been talking about this whole time, but have never gotten to discuss as linear. So this has gotten us to a part of theory where we can start discussing a broad spectrum of different types of functions we've been seeing so far in mathematics. But that'll do it for today's video. Thank you so much. Have a wonderful day.